Once water enters into the soil, it can move through the soil from gravitational pressures, for example, but also water can move from the soil to the roots of a plant. Now, water moves from soil to the roots of transpiring plants by flowing from high to low water potential. And that's always going to be the pattern, regardless of where water is flowing. It's always going to go from high to low water potential. The start of all of this is that roots are acquiring water. And we'll discuss why water flows to roots soon. But once you understand that roots are going to be acquiring water, then it's important to think about the dynamics of water along these thin films. So if you have a root in soil, and there might be root hairs that are coming off of it, you're going to have soil particles. And on the soil particles are going to be films of water that might be relatively thin or relatively thick. When they come in contact with a root, you're going to get movement of water along the surface of the root before it enters into the root itself. And it's one thing that's important for thinking about flow of water from soils into roots is that you need continuous water films. If that film of water is broken and there's a disconnect between the root itself and the water that's out there, then that water has to evaporate in order to make the jump. And so you have to have a continuous film of water for it to flow along a potential gradient. Now in saline soils, soils that have a lot of solutes in there, there's an additional factor to think about. So water in soil, if it has relatively few solutes in it, will be at a relatively high water potential. And again, we said somewhere on the order of 0.03 megapascals. And then the more solutes it has in it, the lower and lower the water potential is, because with a high solute potential, with a high solute concentration, you can think of it as those solutes are starting to pull hard on the water. And so saline soils that have a lot of salts in it, that water is going to have a relatively low water potential. And it could be -1, it could be -2 megapascals, for example. So the saltier the soil is, when roots enter into that water and start to pull on it, they're going to have to pull even harder. And for a given amount of pulling by those roots on the water that's in there in a saline soil, it's going to be able to pull less of that water out than in a soil that's not saline. Another factor to think about for roots pulling on water and moving water from soils to the roots and into the plants is the rooting depth. So a shallowly rooted plant, for example, if that's your soil surface, really only has a small volume to pull on, to acquire water from. And then water would have to be supplied by something like capillary action, which is just not that efficient at moving water long distances. If there is water in deeper soils, putting roots deeper and deeper into the soil gives you a much larger bucket of water to pull from. Now, different species have different ways they allocate roots below ground. And standardizing for the amount of root that you find, on the x-axis here is cumulative root biomass. So 1 represents all of the biomass of a plant, 0 means no root biomass. And then you can look with soil depth here what the cumulative proportion of root biomass is found at 0, 50, or 100 centimeters, for example, for grasses, trees, and shrubs. So at 50 centimeters, for example, a typical shrub would only have 60% of its root biomass, while the typical tree might have 80%, and the typical grass 90%. So what this is trying to show is that there's a lot of differences among species. For these different functional groups, these different types of plants, grasses tend to be more shallowly rooted than shrubs, and trees intermediate. This has been quantified before. This is from a synthesis that shows the maximum rooting depth for different types of vegetation. And you can see that when they look in the boreal forest, for example, or in croplands, the maximum rooting depth is often just 1 or 2 meters. Same thing with tundra, which is even shallower. You might have a maximum rooting depth of only 50 centimeters. Temperate grasslands would be around here, and most, probably half of those grasslands that they've looked at, only have roots that go down somewhere on the order of 3 meters, although you can find isolated examples of grasslands that have roots 5, 6, 7 meters. At the other end of the spectrum, you can find plants in deserts, shrublands, and tropical savannas that have their roots in excess of 20 meters. The deepest root in the world that's ever been found was from a wild fig, and that was found in Echo Cave in Mpumalanga in South Africa. In an Echo Cave, if you go down into the cave, you are 100 meters below ground, and when you're in that cave and you look up, you will see the roots of trees like this wild fig. And so the maximum rooting depth that you can get for a plant is somewhere on the order, as far as we've found so far, of 100 meters. And in some desert systems, you can find roots, when they dig wells, in excess of 50 meters. So some plants have the ability to produce roots at very, very long depths. And that really allows them the opportunity to generate a deep bucket. And in this case, when we're talking about the amount of water that's available to plants, if you are shallowly rooted and your roots only go down this far, the total bucket that can be filled with water is relatively low. But if you can produce roots at a much deeper depth, suddenly the bucket becomes a lot bigger. And the amount of water that you can access as a plant increased greatly.